can I use KSP to compare solubility? We have already mentioned that, KSP is related to solubility. Can I just say that I don't need to calculate solubility? Can I just use KSP? If you have a bigger KSP, means that you're more soluble. Since KSP is related to the amount of ions in solution for saturated solution, so does it mean that if my KSP is big, then this will represent a bigger concentration of ions in solution for a saturated solution? That means the solution actually can hang on to more ions, agree? And this will suggest that, since this solution can dissolve more ions, I can hold more ions in solution, so this will mean that your salt is more soluble. So in general, it makes sense. The bigger the KSP, the more soluble the salt. In general, this makes sense. But we have to be careful with salts for one reason. We will talk about it, which is here. Now, let us try to put in all these values that we have calculated previously. We have calculated all this for the previous exercise. What we are doing is we're just putting in all the values. So involving AgBr, my KSP is given 5.35 times 10 to the power of minus 13. Calculated solubility is 7.31 times 10 to the power of minus 7. Your silver carbonate, KSP is 8.46 times 10 to the power of minus 12. Calculated solubility is 1.28 times 10 to the power of minus 4. And if you take a look at this, maybe we look from the perspective of my carbonate. So for my carbonate, my KSP is 10 to the power of minus 12 versus 10 to the power of minus 13. It is a bigger value. Solubility is 10 to the power of minus 4 versus 10 to the power of minus 7, which is also a bigger value. So it seems that it is true. If you have a bigger KSP, so you'll be more soluble. So you notice it's not wrong for us to say that. But what is interesting is the difference is actually not proportionate. For KSP involving silver carbonate, it is just 10 times larger, but solubility is 1000 times bigger. There's a disproportionate difference if you look at KSP versus solubility. And if the change is disproportionate, then it's not so reliable when we want to do comparison. Now, the reason why there is a disproportionate change is because of the number of ions dissociated is different. I have this here. When we refer back to the previous exercise, when we do the calculation, it's actually very, very obvious. Let's come back to this and we take a look at this. Involving A, how many ions I dissociate? I get 2 ions. So how do I convert KSP to solubility? I have a square root, power 1 over 2. If it is 2 ions in solution. Now, what if I have 3 ions in solution? Involving the second example, if I have 3 ions in solution, how do I do the conversion from KSP to solubility? This is a cube root power 1 over 3. So it means that if I have 4 ions dissociated, then the conversion will be power 1 over 4. KSP to solubility will be power 1 over 4. 5 ions in solution, the conversion from KSP to solubility will be power 1 over 5. So mathematically, the conversion is different. That's why when we look at this comparison, when I look at AgBr, convert KSP to solubility, I do a square root. The second example involving your silver carbonate, KSP to solubility, I do a cube root. So because the conversion is different, and therefore the difference will also be disproportionate. And because of that, we might have instances where you have a bigger KSP but turns out to be less soluble, or smaller KSP turns out to be more soluble. Then the comparison will not be reliable. That's why we have to be very careful with this. In general, when we do direct comparison, if the number of ions dissociated is exactly the same, a ratio of the cation and the anion dissociated is exactly the same, then I can do a direct comparison. If 2 salts give me 2 ions, each salt gives me 2 ions. Salt A gives me 2 ions in solution, salt B gives me 2 ions in solution. Then mathematically, converting KSP to solubility is the same conversion. Both of them are the square root. So the change will be proportionate. And so therefore, what I can do is I can do a direct comparison. If you have a bigger KSP, it means that you're more soluble. So fairly simple. If let's say both salts give me 3 ions in solution, correct? Salt X gives me 3 ions in solution, Y also gives me 3 ions in solution. Then conversion-wise, from KSP to solubility, both will be a cube root. And therefore, the change will be proportionate, and I can do a direct comparison. Bigger KSP means that you are more soluble. I don't need to do calculation. If the number of ions dissociated is exactly the same, there will no problem. But if I consider number of ions dissociated is different, one salt give me 2 ions, one salt give me 3 ions in solution, then we will not be able to use KSP to directly determine or compare solubility. What I have to do is I have to do by calculation, which is actually not difficult, it's just a little bit tedious. So maybe we have an example here involving the first 2 salts. So this AgCl versus Ag2CO3. So let's take a look at AgCl. AgCl, my solubility product is 10 to the power of minus 10 versus 10 to the power of minus 12. So solubility product for silver chloride is actually bigger than the other salt. But if I look at solubility, both of them, the power term is 10 to the power of minus 5. But solubility, this is 1.3 versus 6.5. So this is where I actually have a bigger KSP, but I have a smaller solubility. It's disproportionate. Again, the reason is very simple. The conversion is different. Involving AgCl, KSP to solubility, I do a square root. Involving Ag2CO3, conversion from solubility product to solubility, I do a cube root. Because of that, the change is disproportionate. So we can have a scenario, which is actually very obvious here. We can have a scenario where I have a bigger KSP, turns out it is less soluble. So for instances like this, when we are comparing 2 salts where the number of ions dissociated is different, then we have to do by calculation. We cannot do by direct comparison.